Hello everybody, welcome back to Human Resource Machine. To start today's episode, I want to go back to Digit Exploder and see if we can do better. Previously, we had two separate ideas for improving the speed of our program. The first one is to subtract by 200 and by 20 at a time. This way it allows us to reduce the number of iterations that it has to go through this loop. The second idea was to unroll the loop so that we can minimize the number of copy from and copy to instructions. Now, the first idea was able to reduce the number of steps substantially, but ultimately it was not able to meet the speed challenge. While the second one was able to meet the speed challenge, but it is extremely repetitive. And also at the end, it was getting diminishing returns. So when we added the last iteration of this, it was only able to improve the number of speeds by 1. And so I don't think we can squeeze any more out of this technique. So I was wondering, why not combine the two methods? Starting with our program where we subtracted 220 at a time, why not try to unroll this loop? Just like last time, the idea is the same. Subtract 200, jump if negative. We can immediately subtract another 200, do another jump if negative, do another subtract, jump again, do another subtract, jump again, and this is it. We only need to do this 4 times because after we subtract by 4 times, the remaining number cannot be more than 200 anymore. So we don't even need this to be a loop anymore. This is the maximum number of iterations that we need to do. That already reduces the amount of unrolling that we have to do to our loop. We don't need to do this 6 times. We only need to unroll this a maximum of 4 times, which we have already. Alright, so now let's work on filling in our cases. The first case is if we've subtracted 200 and that's negative, which means our number is between 0 and 199. So in that case, let's add back our 200 to make sure the value we have in our hands is positive. But actually, if we are already storing and not modifying the value that we store, we don't even necessarily need this because we're going to copy from 0 for the next step anyway. So okay, I guess we don't need to do this. So there's basically nothing to do here. The next one is when we've subtracted 200 and it was still positive, but next 200 it became negative. This means we have successfully subtracted 200, so we want to bump the count, the hundreds digit, up by 2. But before that, we want to add back the 200 to make sure the value in our hands is positive and store that back in the slot so that we can work on it later. The next case is 400. Let's do the same thing. Now we're going to bump it 4 times. And then after this, we need to jump to the place where we start working on the next bit of the program. All right. The case before that is 600. Now there is a faster way to do 600 without bumping it 6 times, which is to bump this twice, and then we will add it to itself 2 more times. So we have 2, add another 2, add another 2, that gives us 6. And then we'll put that into the slot. This way we get 6. And we'll jump down to, no, not here, here. Final case is if we have subtracted 800 and the result is still not negative. So we will copy that to 0, and then we will set this value to an 8. And there is also a faster way to do that, which is we copy a 10, put it in here, and all we need to do is bump this down twice. And then jump to the end. Alright, it's still quite a bit of program, but it's not nearly as repetitive as our other version. See how much this is compared to how much this is. The program is already much shorter. After all the 200s are done, we have the logic to handle the 100s. This doesn't need to change, and this doesn't need to be a loop either. We have everything handled here. Oh yeah, here this output, we can put that at the end. So this is where we do this. Yep, that saves us 2 more instructions. And then for the loop where we subtract 20, I'm going to do the same thing to completely unroll this loop. Alright, I think I got the entire program unrolled, so there are no loops now. Let's try it. Alright, see, we reduced the number of steps significantly more. And this is with significantly fewer instructions too. With our with our other version where we were unrolling the loop, that one took 116 instructions, but with this technique we reduced it down to 105. So this is much more efficient than this. Alright, I am happy with that result. Next up, we have the speed challenge for Prime Factory to do. For Prime Factory, the main reason it was taking a long time is this division loop. So it was taking the input like 20 and it was dividing by 2, dividing by 3, dividing by 4, dividing by 5, etc. Now there is a case where if the number is a relatively big prime number, like 17 for example, then it has to go through 2, 3, 4, 5, 6, 7, etc. all the way up to 17 and only then find that it doesn't divide by anything and send 17 to the output. Now there is a common trick used in this kind of prime factor finding algorithm, which is you don't need to divide up to the input, you only need to divide up to the square root of the input. So if it's a 17, then you don't need to divide up to 17, you only need to divide up to 5. And if 17 is not divisible by anything less than 5, then you can be sure that it's not divisible by anything bigger than 5 either. There's a mathematical reason for that. It should be obvious if you just try it yourself and see how it works, but if you have one divisor that's greater than the square root, then the other divisor has to be less than the square root. You can't have 2 divisors that are both bigger than the square root. And so you're guaranteed to be able to find some divisor less than the square root if it's divisible by anything at all. Now one kink in the program is the instruction set doesn't let me calculate the square root of numbers. But that's okay because I am going to do it the other way around and make a cell hold the value of divisor squared. That way, instead of comparing the square root of the number against the divisor, I will compare the number with the square of the divisor, and it's the same comparison. It's just everything squared. So our condition is going to be, instead of input being greater than, or divisor being greater than input, I'm going to check if divisor squared is greater than input now. And if it's negative, I will have to output. So copy from my input, copy that to the outbox and continue. And because I did that in the beginning, I have to insert a jump here so that the program starts at the right place. But yeah, this is the modification that I'm going to make. And now, of course, I need to calculate divisor squared. So initially, divisor is going to be 2. And so I am going to add another 2 to itself, and I'll put that in divisor squared. So divisor squared initially is 4. And then every time, where do I update the divisor? Here. Every time I bump up the divisor, I'm going to have to update divisor squared as well. I'm going to do that by getting the previous square and add 2 copies of the divisor. Put that back here and then bump that up by 1. And this works because just trust me on that. With that, I think should be good. Let's try it. Uh-oh. I outboxed 1. Yeah. I noticed it wasn't stopping because it had 5 in the number, and divisor and divisor squared were more than 5, and it wasn't stopping. So I have to check why it wasn't checking the condition properly. So subdivisor squared, it is subtracting correctly. This is coming from the case where it's successfully divided. This is the case where it updated the divisor, so this should also check that. And oh, this is jumping down here, so this should now move up here. Because originally, when we were only checking against divisor and not divisor squared, we didn't need to check this condition. This condition didn't change anything about our input number. And so we didn't need that, but now we do need to do that because every time we update divisor, it's possible that divisor squared goes above input and then we need to stop. Now for 11, notice that it only goes up to 3, and as soon as divisor gets to 4, it should just bring 11 out to the outbox and skip the rest of the steps. Perfect. Alright, we smashed the speed challenge. Excellent. The last level is sorting floor. Hey, check out this new office. We've really climbed the corporate ladder together. Thank you. My supervising skills truly are adequate. Your skills are pretty good too. Whatever it is you do over there. So are you ready? Oh, they give us a starting program. That's nice. For each zero terminated string in the inbox, sort the content of the string, smallest first, biggest last, and put the results in the outbox. Repeat for each string. Oh yes. Ah yes, sorting algorithms. You can spend an entire semester in school to study different sorting algorithms, and some of them are better than others. Okay, so they give us a program to basically copy the string out to the floor, I believe. Copy from 24 as a 0, 20, they're using that as the index. That is a really ugly index, but anyway. You get the inbox, copy to, yeah, this just copies it to the floor. Now we need to do the actual sorting. Now there is an algorithm called quicksort, but that one is not actually very good for this scenario. Number one, because we don't have very many things to sort to begin with. And number two is because it needs to be able to divide by 2 basically to get to the middle of the array. And we don't have a good way to divide by 2. So what I'm actually going to do is I'm going to start at index 0. I'm going to scan through the entire thing, find the smallest one, and that for the smallest one I'm going to swap it into slot 0. And then I'm going to move on to slot 1, scan the rest of the array, find the smallest one remaining, swap that one into slot 1, and keep going until I reach the end. I think that will be the fastest way to sort arrays given the tools that we have. Alright, so let's rename this, I'll just call this I because that's what I would normally write if I were writing a real program doing this. And then this one I'll call J. So I is the starting index, the index where I will ultimately swap in the smallest number, and J is the one that I'll use to scan the elements. Let me reset I, and then I will have a loop where I'll do whatever. So swap smallest. This is what I'll do inside the loop, and then at the end of the loop I'm gonna bump up I, and then I will check if copy from index I, and I would check if this is 0. If this is 0, then I am done with the entire loop because my I has reached the end of the array, and here is where I will output. If it is not 0, that means we're not done yet, and I will go back to here. This is our I loop. Now, J loop. Inside here we need our J loop. So I will copy from I, and I will have another slot where I store the smallest value. And so my smallest value by default is always what I already have in I. And I will also copy to J, so that initially both smallest and J have the index where I'm starting my search. Yeah, this is where I'm writing my program. I will bump J up by 1 and get the value at index J. Now if this one is 0, then I am done with my comparisons. So I can go and update I and do the remaining work. If J is not 0, then I will compare that against what I have in my smallest. And if this is negative, that means my current smallest is actually bigger than what I have in J, which means I will want to actually do my swap. But if it's not negative, that means my smallest number is still smaller than what I have in J, which means we're all fine. Then we can go to the next value of J, bump J up, and look at the next one. Alright, now for the swapping. We need to swap J with smallest. So actually, all I need to do is copy from J and put that into smallest. Yeah, technically this is not swapping yet. I'm just recording which one's the smallest. And the smallest in this case is what I have just found in J. After I finish this loop, this is when I need to do the actual swapping. I have scanned through the entire rest of the array. I found my smallest. And now before I go to the next index, I will swap that number in. So we already know how to swap from one of the previous assignments, 3-sort. Yeah, that one was sorting 3 elements, but here we are sorting many elements. So I'll copy from, let's see, index I, put that in a temporary slot, copy from index smallest, and put that into index I, and then I will get back my temporary slot and copy that to index smallest. So now I have swapped places. Let's say I is 0 and I found the smallest value here. I'm going to swap the value at 0 into this slot and then the value at 3, which is the smallest, into my slot at I. I think that should be enough, unless I've totally forgotten something, which is entirely possible. Now the output is basically going to be the same as the input, so I will reset the index back to 0 and then copy from index I, send that to the outbox, or I guess jump if 0. If it is 0, then go back to the beginning, all the way to the beginning to work on the next array. If it's not 0 yet, send it to the outbox and then bump up I and repeat. Try it. So far so good. Oh, no. It is only comparing one element at a time. I am not incrementing J for some reason. Bump up J. Yeah, if it's negative, copy from here, but I also need to jump. Yes, I'm not going back to the incrementing J. Okay, that should be right. Let's try it. Yes, now it's comparing everything against the first letter. Yes, now it is looking good. Oh, it's giving me a big array. Alright, we did it, but size and speed could take some improvement. So let's work on the size first, because that's usually easier than the speed. And in terms of size, the thing we can do is not keep track of which one's the smallest. So if we disregard speed, then we're keeping track of the smallest so we can wait until the end to do the swapping. But there's no reason to wait until the end. If we swap the smallest immediately, let's say we do that here, then we make sure the value at slot I is always the smallest one that we've seen so far. Every time we see a value that's smaller, we always swap it in immediately. Then there's no need to keep track of which one's the smallest anymore. This one is swapping I with J, and here the smallest is the value at slot I, because we've been swapping the smallest value into I all the time, and there's no reason to initialize smallest. So that saves a few instructions. Let's see if we can find some more. Okay, here I see copy to I and then copy from I. This looks kind of redundant. So let's see if in this branch when we jump up we also have the value of I in our hands. Okay, almost. We have bump plus I. This will give the value of I in our hands, except we also need to check if I has reached the end of the array. So I wonder if we can move this up. Let's see, where are we? Copy from I, copy to J. Let's say we get rid of this. So we have the value of I in our hands, and then after copying to J, we do the comparison with I. And I believe, yeah, jump if 0 also goes up here. So down in this branch, we bump I, but we don't check if it's 0 immediately. We jump up here, copy it to J, that doesn't matter. And then this is when we compare and see if it's 0. If it is 0, then we're done with the loop. So I think that loop is still okay, and that saves us one more instruction. Yay, we got the size challenge. And the speed actually became a little faster too for some reason. That I did not expect. Oh well, I guess the episode is long enough for today, so as usual, I will leave it here and come back tomorrow to work on the speed challenge. After that, once we complete the speed challenge, this will be the end of the game. Looking forward to that. That's it for today. Thanks for watching. See you next time.